right, let's do this thing. So, yeah, like David said, we'll just take about, every half hour a little time for questions. Are you guys seeing my screen all right, David? Shirag, everything's good?
Yep, all good.
All right,
Yes.
thanks. All right, let's get this show started. Well, first of all, thank you all for joining. Looks like we have almost 300 people in this webinar now. So just want to say thanks so much for showing up. I didn't know that this was going to sort of get this big, so to speak. So, I'm really pumped that I'm able to talk to so many people tonight about something that I really love. So over the next hour and a half, roughly, you'll hear a lot about the aurora, a lot of science, a lot of tips on forecasting and photography, a little bit about what's going on with the solar cycle and basically everything in between. So just some logistics. If you're new to Zoom webinars, you can interact via a Q&A chat, which will be moderated. And I won't be seeing those in real time necessarily, but I'll try and take every 30 minutes a little pause to address some of the questions that were put in there. So that'll also be a nice time where people can take some breaks if they need to. It's a 2-hour lecture. So if you have to take a bio break or get some water or coffee, feel free to step away during those Q&A times. All right, let's get started. So the title of my talk is The Aurora, Nature's Most Spectacular Light Show. And my name is Vincent Ledvina, and this is in partnership with the AAA. So thanks so much for the AAA for inviting me here and giving me this opportunity to speak to you all. So here's just a little outline of what I'll be talking about today. So we got a lot on the plate. First off, I'll just tell you a little bit about me and how I got into this position with auroras and, what's really motivating me and driving me to do all this. And then I'll get right into what is space weather, what is the aurora, when the sun gets angry. So, what is extreme space weather or severe space weather? How does it affect the Earth? Forecasting the aurora chasing and photography, weird kinds of aurora, and about citizen science. And finally, if we have time, I'll just show some cool aurora photos and videos I've taken over the past few years. So right off the rip, we have 2 aurora photos here. These are, most of the photos in this presentation, all the photos of the aurora are ones that I've taken. And these were from Churchill, Manitoba in March of 2022. You'll see some more from Churchill throughout this talk. So a little bit about me. This is kind of my aurora origin story. I grew up in Minnesota, in Maplewood, Minnesota, in the Twin Cities. Hopefully there's some Twin Cities representation here. I saw my first aurora in 2003 when I was 4 years old. So if you remember the Halloween storm, if you're a space weather enthusiast, that will definitely ring a bell. That was my first aurora experience. And of course, I didn't pick up a physics textbook the next day. I was 4 years old. I didn't go to UAF for grad school when I was 4 years old, but I think, seeing that aurora, it was beautiful. And, I can actually remember it. I can actually remember seeing it in the sky. And I think that really embedded this kind of natural passion for the night sky, for STEM, for science and technology, math. And I was, a nerd growing up. I think that experience with the aurora in 2003 is really what started everything. So I was, thankfully, for my parents, bringing me outside camping and for, going down on family trips and just seeing the world, was just really into the night sky. I would go camping as a Boy Scout, as a Cub Scout, and just see the night sky. And in Minnesota, it's just beautiful. So I really became interested in photography in middle school. I just kind of carried around this old point and shoot camera, and then later upgraded when I was 15 years old to something a little bit more substantial. That's really when I got into astrophotography, Milky Way photography. Chasing the aurora, I think, is kind of like the pinnacle of astrophotography. It's taking what you can always see, which is the Milky Way in the night sky, and then, how do I see this rare phenomenon? Like, how do I actually research that and look at space weather? So I went to school in North Dakota at the University of North Dakota to study physics, and that was a great place for me to sort of really unlock my passion for aurora photography. It was as close as I could get to the aurora. My parents wouldn't let me go to Alaska right away. So even though UAF was on my radar when I was 15, 16 years old, I had to settle, quote unquote, for North Dakota, but it ended up being a great time. So at the University of North Dakota, I was really involved as much as I could be. And this is where I got the Aurora Guy moniker. So actually the story goes that, this was, in 2021, I really wasn't on social media. I was kind of getting on social media, but not quite there yet. I kind of decided, okay, I'm going to, it's COVID time. I'm going to try and post my photography, see what people think. So there was this one storm, October 10th, 2021, and I took this aurora photo on the right, which you see, and it was reposted by UND, University of North Dakota. It became their most liked photo ever. And I remember it was the weekend, and I got approached by, all these people on campus and they asked me, "Hey, are you that Aurora guy?" And I was, at first I was like, "What the heck are you talking about? What does that even mean?" So, after asking them, they said, "Oh yeah, we saw your photo on Instagram. We saw that you and Deere posted your photo. You're that Aurora guy." And then, after the third group of people came up to me and said the exact same thing, all my friends are teasing me now. I said, "You know what? Maybe I am the Aurora guy." So that's where that name came from. And then I just have embraced it ever since. And it really is my life at this point. Everything kind of does tie back to the Aurora. I study it in school. I do this, Aurora chasing on the side as much as I can. I'm always kind of tuned into space weather as much as I can be. And a lot of my friends, actually the majority of my friends now, I've met through Instagram, through photography. So, the Aurora can really change your life. And really my motivation for all of this is if you want to see the Aurora, it should not be this mysterious sort of, hard to understand concept. It really is simple if you can find the right person to explain it. And I'm trying to be that person to sort of break down these scientific concepts in a way that everyone can understand. So here are some Aurora chasing adventures I've had over the years. This is actually Churchill and that March trip I was talking about earlier. So went with a bunch of friends up to Churchill, Manitoba, and it was pretty awesome. If you haven't been, yeah, it's definitely an experience. We took the train from Thompson, Manitoba. This time it was only 20 hours, but in September of 2022, actually the same year, so this was March of 2022, I did the trip to Churchill again. I was only here for a week the first time, but I went for 3 weeks in September, and I took the train from Winnipeg, and that is a haul. That one's 40 hours. So if you like trains, this is definitely the trip for you. Here's the September trip. So saw a lot of polar bears. The fall is kind of a good time for that. So if you're into sort of extreme aurora chasing, I mean, here in Alaska, we have grizzlies and moose to worry about, but they're usually, mostly avoidant of people. In Churchill, these polar bears definitely are more of a threat. So different kind of experience chasing in Churchill, but definitely one for the bucket list. And I've thankfully really privileged and grateful to have been involved in this sounding rocket campaign, actually as an undergrad. So a big shout out to Dr. Liz McDonald, who kind of got me involved in this project. I don't know if you're watching, Liz, but through Aurorasaurus, I was kind of looped into this lost through auroral microburst pulsation sounding rocket. So I was up in Fort Yukon, Alaska, at this Air Force base you can see here in the distance for 3 weeks running instruments and collecting data. And then when the rocket finally flew over, I was out there operating all the instruments, and I flew back down to Fairbanks. So I was up in Fort Yukon for 3 weeks. This is kind of my first time ever in Alaska chasing the Aurora. Chasing the Aurora, at higher latitudes is a completely different experience than what you can see and what you can do down in mid latitudes like in North Dakota. So this is really what convinced me to move to Alaska and go to school at UAF. And here on the left, I'll just scroll back here. This is a video, real-time video of the Aurora that you can see pictured on the right. So really, this was a really transformative experience for me. And now, space physics PhD student at University of Alaska Fairbanks, living in North Pole, Alaska. So I've been traveling a lot this year, and you wouldn't believe the amount of times the sort of immigration people, haggle me about, oh, you live at the North Pole. Well, that you can't do that. And I'm like, no, the town is actually called North Pole. And I'm just sharing my love for the Aurora. That's really what I'm doing. Whether that's through science, whether that's through research, or these sort of public talks, that's really just my life. I'm also just recently I've been appointed and invited to this space weather advisory group. It's a federal advisory committee that serves the White House. I'm really excited about this new appointment. I'll be serving in the student representative role for the next 3 years. So actually, just on the bottom here, it's a picture of me in this White House room. So I got to visit the White House last month. That was really, really cool. I'm a photographer, of course, citizen scientist, and I'm researching auroras. So I won't be talking too much about my research necessarily here, because it is a little bit more top level. I'm going to try and keep things a little bit more digestible for a general audience. But I do stuff with auroral beads, and also going to be moving into analyzing rare auroral phenomena with participatory science data. So now I'm going to try and play this YouTube video. If you can't hear the audio, let me know.
Yeah, we can't hear the audio, Vincent.
Don't hear the audio? Okay. Let me. Okay, we're just going to skip it because just for time, it's probably better. Anyways, that is on YouTube. Let me just go back really quick. I can't go back. It's fine. So that's on YouTube, and if you just Google Vincent Ledvina Aerospace Corporation interview, you can kind of get a flavor for the PhD research I'm doing. And I'm also an intern at the Aerospace Corporation right now, which is really really cool because I'm mostly exploring the applied side of space weather and sort of auroras there. In fact, there is an applied side. So by applied, I mean really, how does this affect the real world? And I know that that's like my mom and my family's question all the time is, okay, yeah, auroras are cool, but how does it affect the real world? And actually, it's really interesting. Satellites and other assets in space can be harmed potentially by auroras if they fly through them or above them. So, anyways, if you want to learn more about that, it's on YouTube. And again, all this, really, all the information here, the links, and all that will be sent out in an email after this. So, let's dive right in. So now we're in the second part of my talk. What is space weather? So space weather refers to conditions around a star like our sun and its interplanetary space that may affect space and ground-based assets as well as human life. And if this sounds kind of like a foreign language to you, really all you have to think of is the aurora. The aurora is the perfect, really, guiding, I guess, guiding phenomenon that kind of explains this sun-Earth connection. When you look up at the aurora, you're seeing all these effects really accumulating into a beautiful light show in the sky. So when I tell people I study space weather and they ask me what is that, I say, well, have you ever heard of the aurora? And of course, that opens up the door. So, really, if you're wondering what is space weather and you want to describe it to somebody, just tell them it's the aurora, and then hopefully you can give some more background if they ask, which you'll learn about here in just a second. It's not just the aurora; it's solar flares, it's coronal mass ejections, big explosions on the sun, these million-degree plasmas, shock waves, giant magnets in space. It's this really exciting field, space weather, that I feel like does not get the attention it deserves. I mean, we all know about terrestrial weather on the ground, of course, rain, snow, wind, clouds, things like that. But space weather is going on all the time and can, affect people in ways that, terrestrial weather, does as well. Like even daily effects can occur due to space weather. So, really one of my goals as well is to better inform people about what is going on in outer space, because we get a lot of information about space weather that's not necessarily factual. We see a lot of headlines like, killer solar flare or killer CME is going to come at us and, bring us back to the Stone Ages and wipe out all internet. But really, it's not that. And if we focus on the aurora aspect, we can really start to understand what is going on with the sun and with space weather. So the sun really controls everything about space weather. It all starts with the sun. So again, just like we have weather here on the Earth, clouds, wind, rain, and storms, etc., the sun creates weather in space too. And the sun, if in case you're not aware, is made of gas and plasma. So it's not like one of these rocky planets like Mars or Earth, or even these gas giants like Jupiter or Saturn. It's a really hot ball of gas, and some of that gas is ionized, partially ionized. So then that's called a plasma. It's composed of layers, kind of like an onion. So ignoring sort of the innards of the sun, the layer that we actually see is called the photosphere, and that's sort of what you're seeing here on the right. If you were to look at the sun with solar glasses, like if you were observing the eclipse, you would see sort of a bite out from the moon, and that would be a bite out of the photosphere that you're seeing. And then, of course, during totality, you're able to see these wispy sort of tendrils coming out from the solar disk, which we call the corona. So the corona is kind of like the sun's atmosphere. It extends and forms a solar wind, which, if you imagine the sun as this hot cup of coffee, this disk of sun, the really hot part, the sort of, the sun itself is sort of this hot liquid inside the cup, and then the steam coming off the top is the solar wind. So you can imagine this corona extends out into interplanetary space, the space around the planets, and forms this constant stream of charged particles with magnetic fields, a sort of sandblasting of all the bodies in space, whether that's an asteroid or comets or planets. And the solar wind can affect planets with magnetic fields, which extend out into outer space. And you'll later learn that's how a lot of auroras are formed. So the sun is magnetic as well. It has a magnetic field, and that magnetic field extends out into space through the solar wind and becomes the interplanetary magnetic field. So that's via the solar wind that magnetic field is transported out throughout the solar system. And the sun is dynamic. It has a solar cycle. It varies on sort of an 11-year time span. It has a solar minimum and maximum. So during maximum, which we are in now, which is one of the motivators for doing all this is a great time to be an aurora chaser because of solar maximum. We have more space weather, we have more activity. The solar wind has more chances that it, instead of blowing gently, there's these strong gusts or fast solar wind streams that come out from the sun. And of course, it's space weather, so we have daily events, as well as sort of these more climatological patterns like the solar cycle. So this is what the sun looks like to us on the ground, right? This sort of white, white, I guess unassuming ball of light in the sky, which you're not supposed to look at. But you can look at the sun if you have special sunglasses on and you're looking through a telescope in outer space. So these wavelengths are mostly blocked by the atmosphere, which is why they have to be observed on satellites out in outer space, outside the influence of the Earth's atmosphere. And what you're seeing here, if we go back to the photosphere image, that's really what this sort of orange, literally it looks like an orange, like the fruit, image is right here. So this is called continuum. This is, you're seeing the surface, quote unquote, surface of the sun, the photosphere, and these little freckles are sunspots, which I'll talk about later. But as you move out in the sun's atmosphere and you observe the corona of the sun and the layers sort of above the photosphere, you start looking at different wavelengths of light. So this is invisible light. But as soon as we put on sunglasses with special ultraviolet filters, we can start seeing the atmosphere of the sun, and we start seeing the sun looking really, really different, right? It's not like this unassuming white ball anymore. Now it's got like hairy kind of fuzz on it. There's big bright points, and if you watch movies, you can see these big explosions coming off, big flashes of light. Those are CMEs and solar flares. And what you're seeing here is the influence of the sun's magnetic field. So as we go outwards from the sun's surface, gravity is not as much of a factor anymore, but the magnetic forces of the sun are kind of controlling how these gases and plasmas are interacting. So these bright points are areas where the plasma is really, really hot. And then, of course, these darker areas are where the plasma is cooler. And here's just a video to illustrate that. So we're looking, this is actually 171 angstrom, so 17.1 nanometers. You kind of get to memorize these things after a long time. But this is the Solar Dynamics Observatory, or SDO, Atmospheric Imaging Array instrument. So this spacecraft, I believe, was launched in 2012 or 2014, can't remember exactly. But it's sitting out in space, constantly observing the sun. And, when you watch movies of the sun, it's just amazing how much activity there is happening above the surface in the sun's corona. So again, you're seeing these sort of bright areas. This is really, really active areas on the sun, really hot plasma that's being lit up. You can see huge prominences that are sort of hovering and dancing above the sun's surface, suspended there by magnetic fields. You can see these huge loops, coronal loops, these magnetic field lines controlling the plasma. You can imagine these are kind of like big waves that the particles are all surfing along. There's a big coronal mass ejection there. So anyways, I'm not going to, let this play the whole time. You can do this on your own, but you can really get lost in these movies. It's just incredible watching the sun. And most people have never seen these images before. It's just kind of crazy that the sun looks like this. So it's just awesome. So now we've talked about the sun, we've talked about the solar wind. What happens when all that energy gets really around our Earth? Well, luckily, all these charged particles and magnetic fields don't just penetrate down, right into our atmosphere, right to the ground, right? We have what's called a magnetosphere, sort of this protective magnetic bubble around our planet that deflects and blocks a lot of this energy, these particles in the solar wind from penetrating into our planet and reaching the ground. I mean, these solar wind particles necessarily wouldn't cause any necessarily damage to electronics or spacecraft, but planets that don't have magnetic fields, including Mars and Venus, have their atmosphere slowly stripped away by the solar wind. So that's actually one of the reasons why Mars doesn't really have an atmosphere right now, is that over the past 2 or 3 billion years, a lot of that's been stripped away by the solar wind because the core in Mars kind of stopped working, and maybe it had a magnetic field and magnetosphere in the past and it was habitable, but because that sort of dynamo quit, its magnetosphere faded away, and the solar wind's just been eating away at the Martian atmosphere for billions of years. So we don't want that to happen, and luckily it doesn't happen because we have this protective bubble around us. And just like a rock in a stream of water, this solar wind flows around Earth in its magnetosphere and sort of compresses it on the day side, or the side facing the sun. So it's kind of pushed in, and then it's sort of stretched out in what we call magnetotail that flows, very, very far anti-sunward around the Earth's night side. And that kind of forms this teardrop shape to the magnetosphere. So, usually it would be like the perfect sort of spherical bubble, like a bar magnet dipolar field. And because of the solar wind pressure, it sort of forms this teardrop shape. Well, we don't get auroras, unless there's some sort of energy flowing from the solar wind into the magnetosphere. So actually, depending on the strength and orientation of the magnetic field in the solar wind, some of that energy can couple and be transferred down. It can penetrate our magnetic field. And you can see here sort of these two weak points over Earth's geomagnetic poles. Well, that's where all the energy flows down into, and that's why we get auroras over the poles. So what is the aurora? Well, in short, it's nature's most beautiful light show, and I firmly agree with that. But in the science world, it's a lot of different things going on. It's a lot of large scale processes and a lot of small scale processes. So we're going to talk about those both separately, because I can kind of I personally think of this as sort of like this coupling between these different regimes. So on large scales, you have the solar wind coming in, hitting Earth's magnetosphere, and a lot of it does get deflected and sort of bounces off. But depending on the magnetic field coming in, if it's pointed south, and I'm going to be going over this later too. So you're going to be hearing a lot of this information repeated or said in different ways. So that's so that people can sort of digest it and get different ideas of what's going on. So if you think this is going fast right now, don't worry, because I'll be revisiting all these topics throughout the lecture. But the solar wind coming in has a magnetic field with it. And if it's pointed south, Earth's own magnetic field is pointed north. So if you've ever brought two bar magnets together that are pointing in opposite directions, that like a north and south pole will attract each other. And you can kind of imagine that in outer space, if the solar wind magnetic field is coming in, it's pointed south and sort of links up with Earth's north magnetic field. Some of the particles and the energy along that magnetic field can then be transferred down into Earth's own magnetic system. So that's how we get magnetic energy this energy from the solar wind into Earth's magnetosphere. And the actual process by which that happens is called the Dungy cycle. And you can see sort of a schematic of that here on the top right. So there's sort of this entire dance. Actually, at this heliophysics summer school I did a few months ago, they actually had us learn a dance of the Dungy cycle, which was pretty fun. You can physically do a dance. It's very entertaining. So anyways, that's the process by which this energy flows into the magnetosphere and gets funneled down over the poles. So the magnetic fields are guiding these particles down into Earth's atmosphere, and they eventually collide with gases and create light. And that's sort of the small scale processes. But on a global scale, we see these two auroral ovals that form, one called the Aurora Borealis in the northern hemisphere, and one called the Aurora Australis in the southern hemisphere. And under these auroral ovals, the aurora occurs all the time here. So the auroral ovals are really biased towards the night side. So you can see here on the day side of Earth, it's sort of this really skinny, faint aurora. So yes, we do get auroras during the daytime. That's sort of the first point of energy transfer when the solar wind first links up with Earth's magnetic field. There's some particles that initially flow in, and then they get draped. These magnetic field lines get draped over the magnetotail, and then there's another magnetic reconnection point that happens later in the tail. Then those particles all come rushing towards the night side, and that's really the primary driver as this tail reconnection. So that's why we have more auroras on the night side than the day side. But if you lived in a place like Svalbard or even northern Alaska, where it's dark enough during the daytime in the winter, you could see very faint, usually red auroras during the day. Now, in small scales, and this is actually how the colors are created, we have charged particles, right? So these charged particles from Earth's magnetosphere, they've been energized by these magnetic fields, are bouncing along, and when they get energized enough, they're kind of essentially they're kind of bouncing in between these two hemispheres, kind of like a bouncy ball. And then if you imagine you kind of give that bouncy ball enough energy, well, its bounce point will be inside Earth's atmosphere. So at that point, it's running into all these gases as you get further and further closer to the surface. And just like a game of Plinko, it'll start colliding with all these different gases at different altitudes and give you a range of colors. So here's really the breakdown here. This is kind of how you build an auroral arc. Is if you have a particle coming in from outer space, depending on how much energy it has, if it's a really low energy particle, it may only make it to this red layer, which is is actually one way that scientists can understand the energy of these electrons coming in is by the color of the aurora that's produced. So if you have really low energy electrons, they're not going to penetrate as far into the atmosphere. You may only get red auroras, which is caused by the excitation of O plus. But if you go even deeper into the atmosphere, you may get greens, and there's sort of a dual reaction between these N2 plus molecules and the O plus, which give you the green colors. And then right below that is a layer of nitrogen, this diatomic nitrogen N2, which only really occurs during strong auroral displays. So you have to get this really strong electron to penetrate all the way down here to get, and it'll actually create all the colors on the way down, but to get this nitrogen fringe. So some people, including myself, like to say that the aurora is like a giant neon lamp in the sky, although the electricity is not coming from the wall, but instead is coming from outer space. So really how this electricity, these electrons coming down from outer space, hitting the Earth's atmosphere, penetrating down, and then colliding with gases along the way, which produce light in specific wavelengths. So green is 557.6 nanometers. I think red is 630.1 nanometers. Blue is 428.7 nanometers. So that's actually something to keep in mind, because we'll talk about not technically an aurora, but another night sky phenomenon called Steve, which scientists learned is not an aurora because it does not produce emission in specific wavelengths, but instead across a wide range of wavelengths. So some rare aurora colors, typically we see green because it is the brightest, and that's sort of where the gas is the most dense. So as you move down closer to the surface, the gas gets denser and denser, and different species of gases will float to different altitudes. So we're talking about altitudes here, anywhere from really 60 to 300 miles, or 100 to 500 kilometers roughly. And these red or purple or pink auroras are kind of special, especially these really monochromatic pinks, because that means that the particles have very low energies. They aren't really able to penetrate down to this green layer. And in my opinion, I think these are the rarest colors, are these really intense red and purple and pink colors. Blue, I think, is probably the rarest color. That's when you have this N2 plus emission at a higher altitude. So usually the green sort of wins out when this blue particle, when this blue photons sort of gets emitted, this green kind of overpowers it. But if there's enough particles raining down into the atmosphere, this can happen during geomagnetic storms, or just sort of on really like under quiet conditions too. But if you have enough particles raining down, sort of like if you drop a big stone into a body of water, you have that initial splash up. It's kind of what happens here is these N2 particles, it's called upwelling, can go to higher altitudes, and you can get blue emission at higher altitudes, which don't get sort of overpowered by the green light. And that's pretty rare. You can see a little bit of that blue emission up here in this top right photo, but that also occurs really close to sunset and sunrise as well. The sunlight, when the sun sets, the upper atmosphere is still lit while the ground is dark in some cases. So that sunlight can actually work to ionize these N2 plus molecules and create the blue light, which we see in the aurora. So here's just a little sort of, in case you're wondering where this is all happening, it's happening in a region of the atmosphere called the ionosphere. So it's named the ionosphere because there's a lot of ions, there's a lot of charged particles in these regions. So just to give you some context, it's 15 to 50 times higher than a plane flies, higher than the weather we experience on the ground for sure, like rain or snow. So we're kind of transitioning from terrestrial weather, which we're familiar with, to space weather once we get to these altitudes. And the ionosphere is full of gas, which can become electrified. So it's a gas, and it's also, there's plasmas up there as well. And, of course, we get the main sort of tricolor aurora, which is this green, red, and blue. I guess you could throw in the pink/white nitrogen fringe as well if you want. And you can see the aurora, of course, if you travel to a place under one of these auroral ovals. So luckily here in Fairbanks, that's where I'm at, is we have aurora basically every single night that it's clear and dark. And during geomagnetic storms, the auroral ovals can expand. You could even see auroras from your own backyard, perhaps, including down in the lower 48 during more intense activity. And, really, what's great is that solar maximum means that we're seeing a lot more auroras, a lot more geomagnetic storms. So you don't necessarily have to travel to Fairbanks or Iceland or Tromsø or, these sort of touristy places to see the aurora. You could potentially see it from your own backyard. And so here are the two auroral ovals. We have an Aurora Borealis and Aurora Australis. And right after this slide, I'll be going into some of the Q&A because I'm seeing the questions coming in. But I live in Alaska and I see auroras every single night. And that's because I live under the Aurora Borealis, this auroral oval up in the northern hemisphere. Of course, there is an equal but opposite auroral oval in the southern hemisphere. And just a fun fact, a lot of times the aurora happening in the northern hemisphere is the same as what we see in the southern hemisphere. So if you see a big burst of aurora in the sky, chances are that same burst is happening in the southern hemisphere. So it's kind of cool because these magnetic field lines, of course, connect both of the hemispheres together. So if you have, a little sort of injection of energy somewhere out in the equatorial region, that'll spread throughout the magnetic field and affect both hemispheres, both auroral ovals at once. So really, if you want to see the if you want to see the aurora every single night, you want to travel to one of these auroral ovals, either the Aurora Borealis or Aurora Australis. So with that, let's take a little bit of a pause, and I will go through the Q&A session, and I can just handle this. I'll just answer 3 questions here. I don't want to take up too much time because I have a lot of slides to get to, and I know that people might be short, so I don't want to run over. So let's see here. Does the aurora actually make noise? If so, have you heard it? So this is a good question. I have personally not heard the aurora. I have, however, heard of people who have heard the aurora, especially when I was up in Churchill. A lot of people up there swear that they've heard the aurora. I am not sure whether it actually makes noise or not. There's actually a really good blog post, however, on aurorasource.org that talks about the history of the sound of the aurora, because there has been some extensive research into it, including sort of these recordings of these accounts of auroral sound from these northern communities, especially in Canada and Alaska. So highly recommend you check out that Aurora Source blog article. I think the answer is that the jury's still out, and we haven't, there's not been a sort of systematic, statistical study on whether or not there's sound with auroras. I know that there's been one sort of semi-credible recording of sound underneath the aurora, and you can hear the aurora induce sound in power lines. That is for sure a real thing. So if you've ever heard sort of this pinging sound or kind of sounds like sizzling bacon and you were near a power line, that's probably due to the aurora. All right, can you explain the stable auroral red arc phenomenon? So that I will explain, but in a later part of this lecture, so just hold on. What is the 11-year cycle based on? I'll be getting to this as well later, but that is based on the sort of solar activity that we see across the board. It's not just sunspots. There's an 11-year cycle when it comes to coronal holes, when it comes to CMEs and especially geomagnetic activity. And the 11-year cycle is really a function of the sun's rotation rate. So if you're an astrophysicist, you might know of the stellar Rossby number. The rotation of the sun, it's not the same at all latitudes. It's just the same as really every other spinning liquid body. And the sun has a magnetic field like a bar magnet. And because of the different latitudes rotating at different rates, what happens is these magnetic field lines get wound up, and just so happens that every 11 years, it's the effect of the magnetic fields winding up and then winding down. So if the sun rotated any faster, we would still get solar cycles, but just with basically a shorter frequency. So, instead of 11 years, maybe it would be 7 years or 6 years. And as the sun gets older and it expands and, we lose our angular momentum, or rather we have to conserve our angular momentum, the sun should slow down and our solar cycle might get longer. So yes, that is a function of, that's how we get the 11 years basically. I'll take one more question here. Are there yellow auroras? So yellow, I know that there's an emission line from sodium, which could produce yellow light, although I'm not sure how much sodium there really is up at those higher altitudes, because sodium is a pretty heavy element. So you'd expect it to be floating around at lower altitudes, because if you imagine like hydrogen and helium, like you're going to find those in Earth's ionosphere, but at very high altitudes because they're super light. But I'm not sure about yellow aurora. I know that you can get yellow for sure. Like you can see yellow aurora, but it's not necessarily like its own emission line. But you can get yellow auroras if it's close to the horizon, just like a sunset will turn like turn the horizon, like orange or yellow or red. There's dust in the air that could skew some of the green to more of a yellow color. And in fact, the actual emission line, 557.6 nanometers, is kind of a yellowy green. A lot of people tend to edit their auroras really blue green, but the actual color of the aurora is kind of like a, I guess, yellowy green, or like I don't know what that color is in like the Crayola crayon box. But yeah, you can definitely get the yellow auroras. But as far as I know, there's not really like one emission line that can actually produce like purely yellow. It's usually a mixing effect, or something to do with being close to the horizon and like dust kind of interfering. All right, well, I'm going to continue here, so I'll come back in about 30 minutes with another Q&A period. So where in the world is best? Well, there's lots of places you can travel to see the aurora, not just the ones here on the list, but really any place underneath the auroral ovals will be good. Of course, it's a little bit easier to travel to the northern hemisphere to see the aurora because, well, there's more land, right? The southern auroral oval is pretty much exclusively over Antarctica, although during the May and October events this year, we did see the auroral ovals come up and briefly kind of graze the New Zealand, Tasmania, Australia sectors. So, it is possible to see the aurora, of course, during geomagnetic storms from places in those areas. And during really extreme events, you could even see the aurora from places like South Africa, or even like the southern tip of Chile. But it's really common to travel to the northern auroral oval just because it's a lot more accessible. And of course, it needs to be dark. So you don't want to go to Alaska during July or June to see the aurora, because you will not, and you cannot see the aurora in Alaska during those months. Really, from August 21st, April 21st is kind of what is considered aurora season up here. Of course, it's the opposite down in the southern hemisphere. And yeah, during the summer, it's just too bright to see the aurora, even if it's really incredible display. So that May storm that I'm sure a lot of you saw, that May 10th, 2024 storm, the Gannon storm, was not visible at all in Alaska, and really anywhere above this, sort of purple, this like deeper shade of purple latitude line. So definitely want to come up during the winter to give yourself the darkness that you need. And also equinox months tend to have slightly stronger auroras. It's called the Russell-McFerrin effect. There's also an equinoctial effect, which is slightly different, but the actual reason why this happens is slightly unknown and kind of ambiguous, but it is due to the tilt of the Earth relative to the incoming magnetic field orientation of the solar wind. It just works out that you're able to get more of these big bursts of aurora called substorms, which I'll talk about in a little bit, during the equinox months. And this is just my opinion, but new moon phases are the best to see the most contrast in the aurora. I think people are way too, just way too focused on the moon phase is kind of what I would say. You can see the aurora for sure during a full moon. I mean, you don't need to travel to Alaska during a new moon to see the aurora. In fact, it really helps to have some sort of moon in the sky so you can see where you're going. It sounds kind of stupid, but it really does help, especially in the winter when there's snow on the ground. You don't need a headlamp or a flashlight or anything to see where you're going under a full moon. And I'll talk about it later, but full moon auroras are actually sometimes more colorful to your eye than new moon auroras. Now, like sort of more middle latitudes, it does help to have a new moon, since your auroras maybe not be as bright and they may be towards the horizon where you have a lot of like mist and smoke and dust kind of obscuring the view. So I will say that at mid latitudes, viewers down there, you may want new moons for your aurora chasing adventures or what have you. Now, common mistake people have or make when they go to Alaska is trying to see the aurora at 5 p.m. And I'm looking out my window right now, and it's, what is it, 3:55, and it's almost dark. I mean, it's almost pitch black here. So, and there's no aurora, right? And why is that? Well, that's because the auroral oval is really biased towards what's called magnetic midnight, but basically, if you can imagine like a straight line from the sun through the Earth, you kind of want to be at that midnight spot. And that'll vary, what time this midnight actually is. It's called magnetic midnight, will vary depending on where you are in relation to the geomagnetic pole and what your time zone is. So up here in Alaska, it's more like 1:30 to 2:30 a.m., but in Europe, it's a little bit earlier than midnight. So that's when auroras are sort of maximized. This, a couple hours before that, that's when substorms, that's sort of the statistical best time to observe a substorm is 1 or 2 hours before magnetic midnight. But that means that in really northern places like Fairbanks, or even more extreme locations like Tromsø or Svalbard, you're not going to see your prime aurora until actual like normal nighttime hours. So I get people all the time emailing me, hey, I'm going to be in Alaska in December. And then they'll say, because of all the darkness, so I can see the aurora. And then, I'll give them whatever advice that they're looking for, but I'll add, you don't usually see auroras at 5 or 6 p.m. It is possible when there's a lot of geomagnetic activity that auroral oval can sort of expand, and you can get some sort of more active auroras towards the earlier times. And that's actually one of my benchmarks is, if the aurora is out at 4 or 5 p.m., I have a better feeling that that night's going to be really good. But usually you don't quite start seeing the aurora until 10 to 11 p.m. here in Alaska. Now, this is one thing that I wish people talked about more, but this is what's called an auroral substorm. This is actually part of what I'm studying for my thesis. So over the course of the night, and this is anywhere under the auroral oval, the aurora will charge up and then explode in what's called an auroral substorm. You'll see this growth phase here. This is an all-sky camera field of view. So if you're not familiar with what these images look like, this is a camera with a lens. And, imagine you're kind of in a planetarium and you're looking up at the ceiling and you're seeing the sky all around you, or you're like laying down in a field and you're seeing the sky all around you. And in these images, this is just a weird University of Alaska Fairbanks GI quirk, but north is actually at the bottom and south is at the top, and then east is at the right, west is at the left. So you can see this huge auroral arc stretching across the sky. These auroral substorms have probably the most visually appealing, dynamically moving, and colorful parts of the aurora that you will ever see. It's when the aurora just kind of explodes. People say, oh, it just went crazy. It started dancing. That's during the substorm expansion phase. And substorms can be divided into different phases. So there's a growth phase where you usually see a thin auroral arc stretching across the sky. And this is sort of the aurora charging up. This usually lasts from 10 p.m. to 1 a.m. And these are all context, this is all context for Fairbanks, Alaska. So these times are really relevant for Fairbanks. And again, this sort of relates back to the idea of magnetic time. So, we're not dealing with local time zones anymore. Now we're thinking about our location underneath the auroral oval and sort of that frame of mind. So the onset phase of the substorm, this is actually what I'm studying for my thesis, is you'll see these beaded structures. It's really hard to see in this one specifically. I should have chosen a different one to highlight the beads, but maybe I can pause it right at the right time. We'll see here. Okay, well, it's difficult. Well, maybe I can go back. So yeah, okay. You can see like these little wavy structures here. These are called auroral beads. These form right before the aurora gets really, really good in the expansion phase. They happen for like literally seconds to 1 or 2 minutes. And if you want to learn more about auroral beads, send me an email. I got a poster at AGU going to DC next month and presenting about that. But these auroral beads are a signature of what's going to come, which is the expansion phase where the aurora just fills the sky. It does something called poleward expand. So you'll typically see the aurora sort of over the course of the night during the growth phase, moving from maybe overhead to the southern sky, very slowly. And then suddenly during the onset and expansion phase, it'll race poleward in what's called a poleward expansion. So in the northern hemisphere, you'll start to see these auroral arcs sort of overhead and then moving, drifting towards the south. Then all of a sudden these beads will form. And typically what happens is one of these auroral arcs will just snap to the north and just the entire sky will rip open with aurora. And it's just beautiful. So that's the expansion phase. That's really what everyone wants to see. And there's a recovery phase usually for the rest of the night where the aurora is just kind of diffuse, patchy, or flickering. There's usually 1 to 2 substorms per night. And now forecasting the lights under the auroral oval is kind of, funny to me because is it really chasing the aurora at high latitudes if it's always out and if there's a substorm every night? I mean, literally you could just wait and be patient and see it. But yes, you can still forecast the lights under the auroral oval. You really want to time when these substorms will happen. So it's a little bit different than at mid latitudes where you're waiting for anything. You're waiting for some space weather activity to occur to increase the chances of seeing aurora at all. You're kind of asking yourself under the auroral oval, well, how good will it get? Because it will always be there. But during active space weather conditions, you'll see really crazy auroras at high latitudes. I mean, like this is a time lapse, not from the October 10th storm, but a few days earlier. And we had some just crazy red colors up here in Fairbanks. This is another one of these all sky cameras, but instead south is at the bottom here, north is at the top. So just a little bit of a switch there. But it is possible for the aurora to be too far south in Alaska during the May event, my roommate went down to the Yukon because it was actually dark there at night. It was not dark here in Fairbanks, but the aurora was pretty much all to the south during that event. So it does take a really extreme event for that to happen. Usually during these polar expansions, these substorms, we see the aurora sort of, it's kind of sizzling in the southern horizon, and we're like, oh shoot, everyone's getting a great show in Anchorage. But then during these substorms, it will come poleward. So you actually see that here. I'll just briefly play this video again. You'll see the southern horizon's full of aurora, and then this aurora just expands overhead and then fills the sky and then moving towards the north. So usually we're fine here up in Fairbanks. It's a common misconception is that, oh, it's a KP5, you're going to be, completely hosed on aurora tonight. Well, no, we're still going to see a substorm if it comes over. But if it's like a KP9, something really, really powerful, of course, KP is not the be all and end all for aurora chasing. But, some really extreme space weather activity will cause the aurora to basically move entirely south of us here in Fairbanks. So what causes these really, really good auroral displays? After all, the aurora doesn't look the same every single night. Well, that's because the sun gets angry. So we have the space weather, we have the solar wind. Remember, feels like ages ago, but just, 15 minutes ago, I was talking about the solar wind. We have the solar wind coming off from the sun, this sort of constant stream of charged particles, this, gentle wind usually, but we can get these gusts of wind or these fast streams of wind that can essentially energize the solar wind and cause more pressure hitting Earth's magnetosphere, and can cause then more energy depending on the field, the magnetic field in the solar wind, to transfer down and to get penetrated down into our magnetosphere and then eventually down into our atmosphere and into the aurora. So we have high-speed streams. These are sort of these fast streams of solar wind. We have coronal mass ejections, or CMEs, big gusts of wind, big explosions into space, like, cannons shooting out cannonballs from the sun. And you can see these in, solar imagery as these literally just looks like the sun's atmosphere is blowing apart. And that doesn't just evaporate and disappear. That charge, those charged particles are coming at us, and we can look at where these big explosions are going with instruments like coronagraphs. And solar flares are just big bursts of light, but they're relevant for auroras and can lead to coronal mass ejections. So again, I just said this, but gentle breezes of space weather can turn into giant storms, right? CMEs are sort of these burps or sneezes of plasma ejecting off the sun out into outer space. And occasionally, they're not always directed at Earth, but they could be. And we use what's called a coronagraph to determine where these CMEs are going. So in space, you have a spacecraft. This is specifically the SOHO spacecraft in the LASCO instrument. So in space, you have a spacecraft that has a camera on it, and then you actually physically have this little this arm with a little disc at the very end, and it's held out in front of the spacecraft, blocking out the sun's bright light so we can see what's going on in the background. And when we do that, we can see that it's not just empty space, but there's all this solar wind coming off, and occasionally we see these big bursts and big ejections called CMEs. And if these are directed at Earth, we'll see basically, since the spacecraft is in it's close to Earth and rotating around the sun with the Earth, we'll see a big expanding cloud called a halo CME fill the field of view, sort of expanding radially outward like a halo from this inner coronagraph disk, this occulting disk as it's called. So if these CMEs are directed at Earth, we can expect them to take usually 1 to 3 days to reach us. And when they hit Earth, some of that energy may penetrate our magnetic shield and really cause the auroras to become enhanced. And these things can cause geomagnetic storms, which can cause these aurora ovals to expand equatorward and bring the auroras potentially to your own backyard. Now, solar flares and CMEs, we need to distinguish because they're not the same. And this is really important. If you're not familiar with solar flares and CMEs, to watch the headlines and see, because people often conflate the two phenomena together, but they're not the same. So solar flares are like paparazzi flashes. They travel at the speed of light. So in 8 minutes, once we're seeing them at Earth, they have already hit us essentially. And they're measured on an A to X scale based on the intensity of X-rays that they emit. So, they're emitting light in all wavelengths. In fact, there's radio bursts associated with these solar flares, but we use X-rays to denote their strength. So kind of like, the hurricane categories or, the Richter scale for earthquakes. It's actually the Richter scale is a better analogy because it's a logarithmic scale for solar flares. So A is the most is the weakest class and X is the strongest. So we typically don't see X flares all the time, but during solar maximum with more sunspots and active regions, especially as they're more complex and magnetically twisted up, we'll see more X flares. CMEs are, again, these sun sneezes, these clouds of charged particles ejected with their own magnetic fields into space. They kind of ride along with the solar wind. And if they're really fast, they can push ahead of the solar wind and reach us in, just a couple of days. And these solar flares that occur may really destabilize parts of the sun's atmosphere and cause these CMEs to lift off and be ejected out into space. And these typically occur around sunspots, filaments, or even just random places on the sun. And we watch instruments like coronagraph, images to see when these CMEs happen. And usually they're pretty obvious, but sometimes you might see like little wispy puffs here and there, and you're like, oh, I wonder if that's a CME or if that's, where is that going? And it is definitely an art, and that's why there's space weather forecasters that are trained in analyzing these images. So just to reiterate, CMEs, not flares, cause geomagnetic storms. Although if you have a really, really strong solar flare in that sunspot where the solar flare came from, that active region where the solar flare came from is, right dab smack in the center of the sun facing Earth, well, there's a good chance of the CME with that, and it's also Earth directed. So if you ever see these big solar flare, alerts or notifications, don't start charging your camera batteries quite yet. Wait until we see the coronagraph imagery to see if and where that CME is going. So coronal holes, sort of the next flavor of space weather that may cause auroras. They appear as dark patches in extreme ultraviolet imagery. So remember, we're looking at images of the sun in different wavelengths, so not just visible light, but extreme ultraviolet wavelengths. And these magnetic field lines are open, so the plasma is not confined and is actually cool, so it's able to stream out, and that's why the image looks dark in those regions. And these fast solar wind streams flow out, and they're pretty fast. The normal solar wind is around 300 to 400 kilometers a second, and these fast solar wind streams can be upwards of 6, 7, or 800 kilometers per second. So they sort of push out, and they form this compression region, kind of like a snowplow pushes snow in front of it. You get this compression region called a CIR or SIR co-rotating interaction region or stream interaction region. They're the same thing. And this compression region may hit our Earth's magnetosphere and cause sort of a pressure pulse. And this compression region is really what creates geomagnetic storms, if coronal holes do. Now, it should be noted that coronal holes don't really cause the most major geomagnetic storms like we had in May and October. Those were caused by CMEs. In fact, a number of CMEs in succession hitting Earth's magnetosphere and causing great auroral displays. But coronal holes usually kind of max out if we're talking about the KP index, maybe a 6 or a 7 out of 9. So, and because these coronal holes are sort of embedded within the sun's atmosphere, they rotate with the sun. So we can see them coming many days in advance. And that's what's nice about them, is that we can forecast their arrival times and when this fast solar wind will get to us, and potentially when the geomagnetic storms will happen. So people like to call these sort of lighthouses. And here's actually an image of the same coronal hole over 6 different months, basically. So the sun rotates every 27 days at the equator, overall latitudes, about 23, 24 days at the equator, about 31 days at the poles. Again, that's that differential rotation. And you can see here, image every rotation, this coronal hole, the same one. And of course, doesn't last forever. It does close up at some point. But if you ever see those 27-day aurora forecasts, and you see like a KP5 or a 6, way out in advance, well, that's because of a coronal hole, most likely, causing that potential activity. It may have caused a geomagnetic storm, and then people are saying, well, maybe in 27 days, it'll cause another one. So that's because these things can last multiple rotations. Now, these coronal holes usually close up pretty quick during the ascending and solar maximum phases of the solar cycle, but towards the descending phases, we can get these really long-lived trans-equatorial, so spanning, across the equator, coronal holes. And that's when the 27-day forecast could actually be used to potentially plan a trip to the auroral ovals or somewhere where the aurora can be seen regularly, because these sort of minor geomagnetic storms, like let's just use the KP index as a, safe, as sort of a, friendly way to, talk about these, but like a KP 4, 5, 6 storm, or I guess, KP4 wouldn't be a storm necessarily, but these sort of low-level events are really nice for high latitudes. You can get some really nice substorms from these coronal holes. So yeah, people can use the fact that these coronal holes don't necessarily close up right away, especially during the descending phases of solar cycles, and plan their trips with some certainty that they'll see auroras that are a little bit above average. But of course, there's just so many factors to take into account, especially the weather, right? You can't plan what clouds are going to do in 27 days here on the ground. So who knows? But anyways, just thought I'd point that out. So, with all this being said, I hope a lot of you saw the Aurora this year. Of course, we've had some pretty incredible displays. Here's just a little, just Googled Aurora, and these were the first things that came up. And this is actually pretty fun. So this is data collected by Chris Wickland, one of my friends, and his team. So these are Aurora reports sourced from X, formerly Twitter. And what I did, so this was actually a Google map, so it's like a .kml file. I downloaded that, wrote some Python code, and animated where these reports were popping up as a function of time. So what I want to do at some point is actually like map what the models were saying of where the auroral ovals would be seen during these times. But it's pretty cool that, everyone saw the Aurora. Well, not everyone, but a lot of people saw the Aurora during this, October 10th display. Of course, during the May storm, even more people saw the Aurora, but I just thought this was a cool animation. And, maybe one of your points is in here too. I don't know. There's quite a bit of number of points in the U.S. I'm sure most of the people here are watching from the U.S. or Canada. But, of course, Europe saw the Aurora as well. It was nice because this storm kind of hit, kind of right, I would say kind of right over here, like, over like the Chinese, Indian sector. And then, we all got to see Aurora, which was nice. Sometimes these coronal mass ejections will hit and the effects don't last more than 12 or 24 hours. So if it hits, during the morning time, or sorry, during the evening time in Europe, that's great for the Europeans. But then by the time it, comes around for the US to have their time in the dark, all the auroras pretty much petered out. So this is a great event. Thousands of people reported seeing the Aurora through this map. But as we'll talk about later, there's other ways that you can log your reports of Aurora for science as well. So, and there was a question about the solar cycle. So here it is now. And where we're at, I think I actually need to update this plot. I don't think this has the October data in it, but we can see that we're at this period of heightened solar activity. And what we're looking at here is the sunspot number. So I just have it labeled as solar activity, but there's a lot of different ways that you can, reference solar activity, whether that's sunspots or whether that's, active regions or solar flux. Like if you're a ham radio operator, you might care about the solar flux index or the 10.7 centimeter radio flux. So there's a bunch of different ways that you can, slice the pie or slice the pizza. But right now we're looking at sunspot number, and we can see that we're really at this time of solar maximum. These sunspots are kind of peaking right now. And of course, we don't know when the exact solar maximum will be. We won't know until, the smooth sort of line here is fully traced over. So we might not know until next year, for example, or later next year. But what's kind of cool is that this solar cycle is a lot stronger than solar cycle 24. So, I started aurora chasing kind of around this time here, which wasn't great because we were on the descending phase of the solar cycle, and solar cycle 24 was kind of wimpy. So I'm pretty excited that we're getting a nice strong solar cycle. This is kind of the average actually, across the last 250 years that we've been accurately recording sunspots. This is one of the more average solar cycles. 24 was a little bit below average, but if we're using sunspot number as a proxy for solar activity, with the increasing number of sunspots, we have an increasing number of solar flares and CMEs. So that's why we're seeing more space weather here at solar maximum, is because we have a lot more of these active regions, a lot more chances for these strong solar flares, which can then produce strong CMEs. Of course, it's not just solar flares that produce CMEs. They can happen at random, from these filaments. I think one of the first videos I showed of, that cool dancing prominence on the solar limb, those things can lift off as well and produce pretty large and substantial CMEs. So, all these kind of, coincide with solar maximum, like the maximum rate of these structures on the sun that could produce CMEs. Sort of maximize around solar maximum. And also these coronal holes, the actual auroral activity graph, if you were to plot that along this same plot, time versus intensity, kind of actually peaks towards the descending phase of the solar cycle. So, if you're thinking, oh, well, we're going to be descending soon, like in 2026, 2027, actually, auroral activity still statistically has not peaked. So this is a great time to be learning about all this stuff because we're still going to see a lot of activity even as we're ramping, sort of winding down on the solar cycle. And there's even some research that's shown that during odd numbered cycles, we're in 25, 25 is an odd number. During odd numbered cycles, we see more extreme space weather during the descending phase of the solar cycle. So it's not over. And we might see another May 10th. I mean, we could very well see another May storm or something stronger in the coming years. So yeah, I basically just said all this. And yeah, these are the predictions. So this blue line here was sort of this quote unquote official panel of scientists predicting what solar cycle 25 would look like. They were a little off, I think is a very nice way of putting it. And we're now experiencing solar activity like we haven't seen since solar cycle 24 in the early 2000s. So, and one other thing I want to mention is if you think, the amount of auroras has increased relative to the amount of activity we've been seeing, well, actually, if you think about it, we're in 2024 where basically every single smartphone can take a photo of the aurora. We're seeing a stronger solar cycle than we have in 20 years. So it's not surprising that we're seeing all these auroras. And now people are armed with, more, really education, forecasting knowledge than ever before as well. Like, there's all these free resources out there, and there's people on social media, all these scientists that are just so knowledgeable and sharing their wealth of information. People are catching every single aurora now, whereas before they may not have known about a substorm or how to read data. I mean, we have more data too, like we have more satellites in orbit. So I've been seeing a lot of things online about that as, people worrying that we're seeing all these auroras and thinking that our magnetic field is weakening, and that's just not the case. So space weather could affect you, and likely you haven't experienced directly any effects of space weather, but during extreme events, it is possible that space weather could affect your daily life. Probably the most effective side effect of space weather could be a polar flight being rerouted. Like if you're on one of those polar flights, maybe from Los Angeles to Dubai, right? That one goes over the poles regularly. During the May event, for example, they actually rerouted all those flights from the Middle East and the West Coast to lower latitudes to avoid unnecessary radiation exposure to the crew and to passengers, as well as to minimize any potential effects of communications between the plane and satellites and the ground being disrupted by all the currents and particles that were energizing the upper atmosphere. So, of course, there's GICs, geomagnetically induced currents in the ground that can form when auroras are strong overhead. If you've ever studied electromagnetism, you have Maxwell's equations. Time-changing magnetic field produces a current, and that current in the ground can travel up through transmission wires and damage power grids. And if there's a strong enough storm, you can have cascading effects as well. And of course, that's not the end of the story. There's all sorts of other things. But I guess I'll leave you with one little factoid, is that during the May 10th storm, because of the increases in basically electron content in the ionosphere, signals from the ground, especially GPS signals, were not able to make it through. They were getting scrambled. So farmers these days use precision GPS all the time in their planting, and they were not able to plant during the May 10th event because they're locked. The GPS lock on their tractors was all over the place. You need inch level precision, and the economic impact from the May 10th event just on farmers in the US was estimated at $500 million. So, we talk about hurricanes and tornadoes and, these types of more familiar weather events causing billion-dollar, effects, right? Well, space weather, that May 10th event easily around the world may have, I think it's safe to assume around the world cost over $1 billion in, economic impact. So I'll take questions after this slide here, but the Carrington event is perhaps the most infamous extreme space weather event. There have been other events more recently than the Carrington event that were stronger, actually. So that's kind of a misconception, is that the Carrington event is this one-off. No, these Carrington events happen more frequently than you probably think, but this is the one that gets reported about the most. And Richard Carrington was observing this large complex sunspot group in 1859 and saw what's called a white light flare. So as I said earlier, flares emit radiation in all wavelengths essentially. But if you have a really strong flare, you can get what's called a white light flare. So you can actually physically see the flare happening. You don't have to look at like a special wavelength. And he observed this white light flare, and then less than a day later, there were auroras seen all around the world. And those geomagnetically induced currents I was just talking about basically traveled up through telegraph wires and damaged equipment all across the US and around the world. So just to give you an idea of how much power there was coursing through the ground, operators were able to unplug their telegraph systems and continue sending messages with just, auroral power, essentially, which I think is just incredible. So, the whole reason why there's space weather forecasting and such a focus on space weather is, what if we had a Carrington event now in 2024? We have a lot more than telegraphs that we have to worry about. So luckily, in my opinion, we would not see a complete blackout or sort of apocalyptic event. We have a good idea of how these things happen, but we haven't had a Carrington event in quite some time. It's been 40, 50 years. So just within that period of time, we've had a lot more technology. We're a lot more reliant on things like GPS, and we have satellites. We have thousands and thousands of satellites in low Earth orbit that can get affected by these big geomagnetic storms. So who knows? We'll just have to wait and see. So, all right, been yapping a lot. Let's take some questions. Just talk, or I'll just take questions for a few minutes here. Let's see here. Can extended prominences or coronal loops near sunspot regions cause CMEs by any chance? Yes, for sure. So I'm not an expert on CMEs and I guess sunspots and things like that. But as far as I know, a lot of these CMEs that occur are actually from prominences over sunspots. So you'll typically get a little small prominence that forms these active regions, and then that prominence is actually the thing that sort of lifts off and produces the CME. So you can kind of, if you look at these active regions, especially from the side, and you don't see one of these prominences, if you have a big solar flare, it may be unlikely that a CME is produced. How strong was the Carrington event when compared to what we've seen recently? Are we protected if another event that strong were to occur? So in terms of the magnetic field of Earth, over the past 250 years, not much has changed relative to the strength of the magnetic field. Of course, it's not been constant. So I was just saying, of course, this is sort of contradicting what I just said, but the Earth's magnetic field, it's the same strength, but it's a different configuration maybe than it was 250 years ago. We always see these things about the magnetic pole wandering, and it's moving closer to Russia now, or it's accelerating here or there. Really, and I'm learning about this right now, so I really suggest people do their own research. But really, what that is the Earth has a magnetic field which has largely remained the same strength, throughout hundreds of thousands of years, perhaps. But the orientation of that magnetic field may wobble or change its components. So, like, we have a bar magnet, that's one component of a magnetic field called the dipole. But there's also other what are called multipole moments of magnetic fields. So it may be possible that the Earth is slightly increasing its multipole moment and decreasing its dipole moment, but the overall strength is not changing. So if a Carrington event were to happen now, of course, these effects are pretty small. So like, we're not seeing any effects really in the aurora, but I mean, if a really, really big event were to happen, it's possible that one of these multipole moments may cause a little spot of aurora to appear like over the South Atlantic anomaly. That's something that people were talking about during the May event. Is there are a few reports of auroras actually over like Peru and like northern Argentina, and there's a little weak point in the magnetic field called the South Atlantic anomaly. So there were some people saying that there were particles being pushed super far in around Earth that were causing those magnetic field lines that map to those latitudes to become energized with particles. So it's possible that we could see some interesting stuff. But we are relatively protected. I mean, I guess to really zoom out here, Earth has taken a beating, over the course of the last however many billions of years, and we've certainly seen stronger events in the Carrington event. If you look at ice cores and things like that, there's some ways to reconstruct, whether we've seen really extreme space weather before. So I think we'd be fine. I don't think Earth is going to get ripped apart or anything like that. I'll take one more because that was a little bit of a long answer. Why are some auroras visible to the naked eye and others only seen with the camera? Well, we'll be talking about this later, but essentially it boils down to our eyes are just not as great as cameras are at seeing in the dark. So some auroras are just too dim for us to see, and our eyes were really never designed to, do aurora chasing. We're designed to see in the well-lit environment of, a sunlit world. So when you stick, really sensitive pixels that can take exposures, 30 seconds to a minute. When you have those in your camera, of course, you're going to see more. So that's basically what's happening. All right, so let's get into aurora chasing and aurora prediction. And the real question here is, can we predict the aurora? And my answer is kind of, but it's hard. And just a reminder about how this all works. And I kind of just like to, frequently remind people where we're at. We are talking about a coupled system here. So we have different regimes that we're talking about. So we have what's going on really on the sun's surface and the sun's atmosphere, the corona, the solar wind, coronal mass ejection, solar flares, how all that energy travels out into outer space, the interplanetary space. We have Earth's magnetosphere. So now we have another regime. So we have all this stuff coming out the Earth. How does the magnetosphere respond? So that's really due to what the orientation of the solar wind magnetic field is, how that all couples, how the energy flows in. And then we also have the ionosphere, which plays somewhat of a role, but largely we neglect that. So now we have, those small scale processes. We have the aurora actually being generated within the atmosphere. So we can measure the solar wind, we can measure magnetic fields in the magnetosphere, and we can really sense the response of the aurora in the ionosphere. And that's how we can use all that we can use all that information then to try and figure out what's going to happen with the aurora. So here are some tools that we use, that I use, that I personally use, especially, the Ovation prime model, real-time solar wind, Enlil, AE index, goes magnetometer. And don't worry, you'll see more of these in the next few slides. So, one thing that we can do is forecast what the solar wind is going to do. So we can look at the sun and we can see these big ejections coming off in coronagraph imagery. We can use fancy equations and models to predict where they're going to go. And then we can run those in models and see, okay, where is that CME going in interplanetary space? And is it going to hit Earth? And when is it going to hit Earth? How strong is it going to get? Or rather, how strong is the impact going to be? We have no idea what the magnetic field is in these CMEs, but we can at least get an arrival time and we can tell, okay, well, it's a really fast and dense CME, so we might get a big geomagnetic storm. Or we can say, well, it's kind of wimpy and it's like a side swipe, so maybe we won't see much. And all models have uncertainties. One tool that's really good, along with Enlil, is called Huxt. And I actually have a blog on how to use the Huxt model for aurora chasing that I wrote in partnership with my friend Tanya Melnick. So definitely check that out. And we have a listing actually on Zenodo for a DOI as well, if you want to cite that. So the KP index is the K planetary index. It measures global average geomagnetic activity. It's only one number every 3 hours. It's average magnetic activity from a chain of mid-latitude observatories. So you can see all of them dotted here in red around the world. It's a global geomagnetic activity index. So it's not measuring localized disturbances, it's measuring global disturbances. It's reported on a 0 to 9 scale, and it links up with the geomagnetic storm scale, so the G scale. So KP5 is a G1, KP6 is a G2, et cetera, et cetera. And actually, fun fact, the NOAA Space Weather Prediction Center, the Space Weather Forecasting Office here in the US, is redoing the space weather scale. So this G scale may be defunct in a few months. So just kind of a little forewarning there. But really, the bottom line is that a lot of things rely on the KP index. So actually, this wasn't recent. This was 2023, but I just went to Chena Hot Springs, and they still have the KP index up there. And it's even worse because it's one thing to put the KP index on a little whiteboard, but now they're calling it the Aurora. I think it's, what do they say? Auroral strength. And it wasn't even updated. It was like from 2 weeks ago. So anyways, a lot of things rely on the KP index. I mean, hotels will have this too. And they'll say, oh, it's a KP5 tonight. I've actually checked in at a hotel and they told me it was supposed to be a KP5. So people know about the KP index. It's used all the time. You've probably seen it. It's in apps, it's on the news, whatever. But there's limitations to the KP index that need to be addressed. And this is kind of, I mean, if you've been following me, you'll know that I have my reservations here. So, really people just say, okay, higher equals better, right? You have a KP9 versus a KP8. Oh, well, it's a 9 and it's bigger than an 8, so it must be a better aurora. Well, not necessarily, right? The KP is a 3-hour average of activity. So it's smoothing over a lot of these little variations, like in substorms, right? You have this, 20 to 30 minute bursts of aurora. Well, KP is not even going to see that. And if something hits Earth, you have this big intensification of aurora. Well, KP is not going to respond until the next time that, index loads in. It's also a global average. So again, these substorms start out small and they spread across the entire world. But when it's this little localized burst of aurora, if it's a really small substorm, it might not even get captured in the KP index, even after the fact. These magnetic stations are not also in the auroral oval, so KP objectively cannot even track auroral activity at high latitudes. And the predictions of KP are more like best guesses, right? So you might see a 3-day forecast that says, oh, there's going to be a KP7 because of the CME that we see coming. Well, that's really just throwing darts at a wall. I mean, obviously a KP9 I would pay more attention to than a KP3, but it's not gospel, as I just said. So here's just that averaging visualized. This is one of the magnetometer stations that feeds into KP. This is the raw value. So imagine you're watching the aurora and it's kind of wiggling around. It's increasing in brightness, decreasing in brightness. It's not just like the static blob, right? It's doing all sorts of things. And that's reflected in the ground magnetometers measuring the magnetic perturbations from what's going on in the aurora and the currents in the aurora above. So the raw value is this sort of black squiggly line. And these bars, these sort of, these horizontal lines are what the KP is saying. So imagine you're opening up your app and you're saying, oh my God, it's a KP5. Look at this. But the actual value is all the way down here. KP5 versus what? Aurora's at, what would this be, right? A KP 0.3 or something. So anyways, it just goes to show you that the KP is not all that it's, basically said to be. So just keep that in mind. Of course, there are some uses for it, mostly in like the space weather, forecasting world, and when communicating with power grids and people in industry and customers, they'll have different responses from different KP thresholds being reached. But in terms of aurora chasing, I would largely ignore the KP index. Now, there is sort of a smarter KP called HP30. This is the KP index, but reported every 30 minutes. So it's possible that you could get some better fidelity in what the aurora is doing by using the HP30 index. Also, the HP30 index is not limited to just a 9. So if we're looking at the May 10th storm, this is the HP30 index. You could say that, the KP, quote unquote, went up to 11, but obviously it didn't max out at 9. But if you look at the HP30, if you were able to sort of extend above a 9, you would get all the way up to 11 in that case. So if you're still kind of, wedded to this 1 to 9 activity scale, that's totally fine. I would just recommend using the HP30. It's just not in a lot of apps, like not a lot of mobile applications, but you can easily Google it and just bookmark it on your computer if you wanted. The Auroral electrojet index is kind of what the KP should be, or what people think the KP is. So what it is, it's a similar global index of magnetometers, but these magnetometers are actually underneath the auroral oval, sort of the statistical average auroral oval, and they're updating in real time. So how you use it is higher number equals more magnetic activity under the auroral oval, and sort of my rough estimate is 500 nanotesla for a good US, Canada border show, and then 1,000 nanotesla for a really good aurora in the central US. Of course, these are just sort of, hand wavy, estimations. You're actually going to want to go out and see what's going on in the night sky rather than just use one number to tell you what things are doing. Now, the real-time solar wind, I mentioned the BZ earlier, but when you have south or negative BZ, that's able to link up with Earth's north or positive BZ magnetic field. And when this happens, you get this process called magnetic reconnection, and that energy from the solar wind can then transfer down and penetrate our magnetic shield and flow into the auroral oval. So when you have BZ south, that's really what you want. And this is the Dungy cycle illustrated here in this nice animation. So we'll see that magnetic reconnection on the day side, these magnetic field lines sweeping out, and then magnetic reconnection in the tail, sending particles to Earth's night side. So these, reconnection events in the tail are primarily what drive aurora on Earth's night side. And you get these magnetic field lines coming in. The magnetic sort of configuration inside our magnetosphere turns from very stretched to more of like a bar magnet dipolar orientation. So that'll make sense here in a little bit when I talk about the GOES magnetometer. But real-time solar wind is relatively, I'm not going to talk about it in depth here. It just is it's such a huge topic. But I do have this ebook, so that's in this ebook I've crafted with basically being a companion to this talk, kind of a beginner to intermediate guide to aurora chasing. It's like 60 odd pages. I actually made it over my winter break just this year, so it's free. Just scan the QR code and you can get it. It'll automatically be emailed to you, and I got all sorts of stuff about the solar wind in here, along with other definitions, because you can only cover so much in a 2-hour talk, even though you'd think you'd cover a lot. You can, but you could talk about this stuff for weeks, for months, for years. So anyways, I have lots of stuff in this ebook about real-time solar wind and how to monitor it and what to watch for, especially looking at patterns in the solar wind for CMEs and coronal holes and things like that. So the Ovation model is probably in all of your Aurora apps if you have one. It's a model of the auroral oval based on solar wind inputs. So there's hemispheric power measured in gigawatts. So higher gigawatt equals more aurora, supposedly. But the problem is that it's a statistical average response. So it cannot detect substorms because substorms kind of happen. The actual triggers of a substorm, like what causes a substorm to occur, I mean, that's under debate in the research community. Like, we don't actually know what causes a substorm. There's a lot of patterns in the solar wind that might cause substorms, but the Ovation model really was not designed for that. It's really just like, okay, well, we have BZ is -50, so the aurora should be good, right? And that's kind of what it's designed for. It's kind of just okay, you load it up and wow, it looks really cool, tons of aurora. But in reality, the aurora is obviously not just a flat donut. It's a lot more structured too. But you can also see aurora further equatorward than what Ovation tells you during these substorms. You get this huge intensification of the auroral oval, but as I was saying, you can build that auroral arc from the top down. All those particles are funneling in, and the aurora physically gets taller. I mean, during these big substorms, and you can see auroras from way, far equatorward of what is being seen here in the model. So this is probability of aurora, but this is during this is what, the 2020. Yeah, so this is the November 4th event in 2021. I remember seeing photos from like North Texas, from Arizona. So you don't see that you don't see that in this model, but you can see the aurora far equatorward of what this model is showing you. And so, how to forecast auroral substorms? This is kind of like the golden question, right? How do we do this? Well, auroral substorms, just as a little reminder, usually only last 15 to 30 minutes. This text box is supposed to say it was photographed by my friend Mike Shumko. This is actually the substorm I saw. If you remember that big auroral spiral, like slide number 4 in this presentation, here's a little time lapse of that. So substorms usually only last 15 to 30 minutes. It's sort of like this rubber band or bucket analogy. You have all this energy building up in the growth phase. And actually in outer space, you have these magnetic fields that are stretching out and all these particles being held back, kind of like you're stretching back a rubber band and you have a bunch of like rocks or pellets or something that you're going to fire at somebody or whatever. And during this growth phase, these magnetic field lines are stretching, and then something causes those field lines to let go of all these particles and they come rushing back towards the Earth. And all those particles get funneled down over magnetic field lines and cause auroras to occur. So, of course, I already talked about this. Bright colors, active motion, causes the auroral ovals to really become energized. You can see aurora hundreds of miles further south or equatorward of the main oval. Might get 1 to 2 substorms on a normal night, 3+ on an active night. And really, my favorite tool now is the GOES magnetometer. And I have a whole blog article on this. So I'm not going to spend too much time here, but what's really cool is watching this video on the right. This is an all-sky camera time-lapse of the aurora over Fairbanks, Alaska. This is actually just fairly recently, last month, October 6th. And you can't really see it well, really, in this plot here. But you can see during these big spike ups in the GOES magnetometer is when all the particles are coming and streaming towards Earth and causing auroras. So let me just kind of, if you watch this green line, this is like the current time in the plot versus the current time in the time lapse. So when this green line reaches one of these big spikes, you can see the aurora just goes nuts. You'll see it here. Boom. Yeah. So it's pretty reliable, actually. I mean, it's not necessarily a one-to-one, like exact minute to minute, reliable. Nothing really is. But you can get a really good idea of how stretched out this tail is, how far back that slingshot's being pulled, and then you can see when these particles are coming in. Because the satellite's actually in Earth orbit. It's measuring how stretched out the magnetic fields around Earth are. So when it's more stretched, the graph goes down, and when it's less stretched, imagine imagine you're taking a rubber band, you're stretching it out. Physically, it's getting shorter, right? So that component that's measuring how tall it is gets smaller and smaller. That's why you see the graph going down. And as soon as you let go of that rubber band with all the particles, it turns from stretched out to very round, and that's why the graph shoots up. So anyways, I got a whole article on that on my website. Check it out if you want. But really what we want is ground truth data, which is you, right? What is the Aurora actually doing? And so you can track auroras with Aurorasaurus. I actually interned for Aurorasaurus back in 2020. It's a NASA citizen science project that is really designed to leverage the power of the aurora chasing community, right? There's people all over the world seeing the aurora, and you can submit your reports to aurorasaurus.org and then see where people are seeing the aurora. There's also webcams all over the world. I have a big list on my website you can check out. And of course, webcams are also great. You can actually see the aurora in real time, and who cares what Ovation is saying or what GOES is saying, right? Let's just watch the aurora as it occurs. So this was kind of a fun thing, is that during the October 10th storm, I was watching these two webcams. One of them was in Maine and one of them was in Georgia. And in Maine, the aurora was to the south, and in Georgia, the aurora was to the north. So if you can imagine, the auroral oval was somehow sandwiched in between Maine and Georgia, which was just wild. Now, here's just a quick comparison. I'm kind of running a little bit behind on time, so I'm going to speed up a little bit. I'm not going to go through all this, but you'll be getting the slides and the recording of this talk eventually. So don't worry if you're not able to take notes as diligently as you normally would. But really, this is just a comparison of all the different sources of data that I like to use and the strengths and weaknesses of them all, and sort of some quick facts about them. So, like, for example, the time resolution of KP is every 3 hours. But of course, if you're watching a webcam that's updating live, it's going to be in real time. You can actually see something happening. And you can go outside and say, oh my God, look at the webcam in Fairbanks, it's going nuts. Then walk out the door and see it right above your head. I mean, I do that all the time. So now, visualizing all these tools from the sun to the mud, so from the surface of the sun to the surface of the earth, you have all these different tools. It's kind of like where they're trying to forecast space weather. So of course, Enlil and different solar wind models are kind of in this interplanetary space. You have real-time solar wind taking data from 1 million miles upstream at satellites, or from satellites at Lagrange point 1, so 1 million miles upstream, kind of giving us a 30 to 60 minute heads up of what's coming in the solar wind. You have Ovation Prime taking that solar wind and trying to model what's going to go on in the aurora. And then you have magnetometers in space and on the ground trying to figure out, or rather monitoring the response of the Earth's magnetic system to all these different solar wind inputs. So you have these different timescales of forecasts, and then you can start to construct. You have a 27-day forecast, which is kind of the maximum timescale you can think of as a single solar rotation, right? I was talking about those coronal holes rotating around every 27 days. You can kind of forecast geomagnetic activity out to that 27-day window. 1 to 3 days, you can start looking at these coronal holes as they're approaching the meridian on the Earth-Sun line. That fast solar wind starting to stream out. You might see a big CME coming off the sun. Those usually take 1 to 3 days to reach us. And then when that solar wind actually hits monitors at L1, that's really when we know what's coming, right? We don't really know what's coming until we get to monitors at L1, this real-time solar wind. And then, of course, what's going to happen with the aurora, that's a completely other question. But we can really kind of develop these different forecast windows. And this is kind of how I think of things, is like, okay, well, 27-day forecast, I honestly don't even really pay attention to at all, because I'm so addicted to this stuff that I'm looking at things 1 to 3 days. I'm honestly just on the real-time solar wind page like every 5 minutes, every 10 minutes throughout the day, just seeing what's going on. But yeah, I mean, you can sort of, if you're trying to plan a trip and you're like, well, I don't know what's going to be good. And, you can kind of look at the 27-day forecast, the 1 to 3 day forecast, and see maybe what's coming. But I wouldn't, put any money on anything until we actually see it at L1, in the real-time solar wind. So here's kind of my high latitude aurora chasing workflow is, basically how good is a substorm going to be, and then also when is it going to substorm, and is it going to be a weak or a strong substorm? And this is kind of my workflow. Then for mid-latitude aurora chasing, it's a lot different because you're waiting for some activity to push that aurora down to lower latitudes. That auroral oval's got to be energized somehow because, I mean, you can get some pretty weak space weather to cause a nice substorm, but it has to be some sort of space weather. So, if you're trying to catch every single aurora, I would really recommend using something like the GOES magnetometer to find out like how charged is the Earth's magnetic field and how big is that substorm going to be. So, there's tons of these questions that I constantly am asking myself if I'm, because I'm also issuing alerts and trying to help people out who are at lower latitudes as well. Obviously, I'm privileged up here in Fairbanks, but the majority of people are not living in North Pole, Alaska, right? They're down in the States or something. So, I'm trying to watch for all this stuff, but you typically need some sort of space weather to see auroras down in the lower 48. And then, of course, before we finish this section, remember it's all up to you, right? There's tons of questions that you need to ask yourself, and that will sort of dictate how dutifully you watch the data, what you pay attention to, who or what you're looking at, and how you respond to different changes in solar wind or in the forecast, right? Because if you're trying to photograph every aurora, well, you might just want to focus on GOES magnetometers and real-time solar wind. But if you're looking for the next May 10th event, there's probably going to be some sort of forecast out for that, right? I would say it's pretty unlikely that we're going to be blindsided by a KP9. So, maybe you just want to look at the NOAA 3-day forecast, and if you see a KP8 or 9, just start paying attention when that forecast becomes valid. Like if it says it's going to hit Sunday night, well, maybe Sunday evening, start looking at the other data, but you don't have to be looking all the time. Because if you've seen the May events and you're like, okay, I've seen it, but I want to know when it's going to get really good like that again, well, maybe you just want to look at specific data that aren't necessarily real time. You don't need to look at everything all the time. So just keep that in mind. So here's some aurora chasing tips and tricks. And I know that we only have 15 minutes left, so I will be speeding up a little bit. I have a whole section on photography, so I might just skip that because it's not really related to aurora chasing necessarily. But the bottom line is that you all can become aurora chasers, and it's probably easier than you think. Of course, choose a dark sky location. The aurora can look very differently depending on where you are in the world. And, if you're at mid latitudes versus high latitudes, it could look like a dull gray glow on the northern horizon to dancing green waves all over the sky. And red aurora glow is really common because you're only seeing the tops of the aurora looking towards the horizon, right? The curvature of the Earth is going to block the green lower altitude emissions, so you might only see the red. And this is actually a picture I took during the May event, the Gannon storm from India. So that's pretty wild. I saw the red aurora in India. So really high altitude emission, but very far away. And of course, we all see colors differently, and of course, our eyes are just not designed to look at the aurora or look, for things in the dark. The night sky, for example. I think we evolved more for other reasons. I don't think aurora chasing was one of the I guess Darwinistic survival of the fittest criteria. So, anyways, it just means that cameras can see a lot more colors in the aurora than we can usually. If the aurora gets really, really bright, of course, you can see more colors in it. And actually, it benefits a little bit to have a full moon or some sort of light source nearby that can trick your cones. So we have rods and cones in our eyes. It actually helps sometimes to have a full moon in the night sky to activate more of your cones, which are the color sensitive cells in your eyes. And that can cause you to see a little bit more color in the aurora, especially when it's dimmer. And again, we all see colors differently, and a lot of people are actually colorblind and they don't know it. So if you're looking at this colorblind test on the left, you're not seeing there's actually a green square in the middle of this gray circle of dots, this sort of gray field of dots. You're not seeing that green square. That could affect your ability to see the really faint greens in the aurora. And some little biohacking you can do, I've done this before, is, you're going to lose your night vision, so just keep that in mind. But shine a flashlight into your eyes to activate your cone cells, allowing you to see colors just really briefly. So now, aurora photography, I'm just going to do the basics here, but smartphones these days can take aurora photos really just point it at the night sky and press go, and it'll probably do a pretty good job. If you have a DSLR mirrorless camera, 5 to 10 seconds is good. Aperture at your lowest f number. ISO will just have to be adjusted to how bright you want the photo. You don't want to be clipping out any shadows or highlights, and then shoot in manual mode as well. I have a bunch on aurora time-lapse photography, but I'll just save you the time, and I'll tell you that I have a whole blog article on that on my website. So just feel free to check out that link. I do a lot of time lapse. I think it's great. It's very computationally intensive and time consuming, but it results in a really cool way to visualize the evolution of the aurora over time, which I think is really unappreciated. Is the aurora is not stagnant; it moves, and it can move really fast. Now, weird kinds of aurora. Um, we have a lot of weird kinds of aurora these days that have always existed, as long as Earth has had a magnetic field, perhaps. But that citizen scientists, that aurora chasers, are noticing more, and then really collaborating with scientists to learn more about. So you've all probably heard of Steve, strong thermal emission velocity enhancement, but there's also other phenomena as well. Steve is perhaps the most viral of these phenomena. It appears as a sort of white arc across the east-west sky. So, the aurora is usually to the north, but Steve usually appears overhead and to the east and to the west after a substorm. And you typically get these little picket fence features as well, along with Steve. It was discovered, first, I guess, written about in 1911 by Carl Stormer, but aurora chasers, primarily in the Alberta aurora chasing community, rose were raising awareness of this phenomenon, and we're collaborating with scientists back in 2018 to really realize that this is not something that's been adequately investigated before. So they worked to publish a paper, and in the process of sort of scientists, grappling with this quote unquote new aurora, or this this strange thing in the sky. These aurora chasers called the thing Steve. And if you've ever seen the movie Over the Hedge, that's where the name comes from. So now we're going to learn about Steve, but we can do that another time. And friends of Steve. So again, Steve was discovered, quote unquote, discovered in 2018, but now we have a whole family of Steves, or Steve's relatives, or whatever you want to call the clan of Steve, the family of Steve, the friend network. I don't know, but we have Ragda, we have SAR arcs, we have all sorts of things. SAR arcs actually have had quite a bit of scientific attention, but recently it was discovered through the collaboration with an aurora photographer down in the southern hemisphere that SAR arcs can evolve into Steve. Auroral dunes are formed by the modification of proton aurora secondary electron emission from proton aurora at lower altitudes, in one of these gravity waves from the lower atmosphere propagating up, forming these striations, which are called auroral dunes. And then my favorite are these FAEs, or fragmented aurora-like emissions, which are kind of like these green tic tacs that are not field aligned. So as I was saying earlier, these electrons come streaming down into our upper atmosphere along field lines. Well, these tic tacs, or FAEs, are really not aligned to those fields, not aligned to those magnetic fields. So they're similar to what's called streaks seen in Steve's picket fence, but it's unknown what these are exactly caused by. So aurora photographers like yourselves, we really, the scientific community is really going to rely upon you to provide observations if you can. And we're definitely looking to collaborate with more people to understand just really the basics about all these rare auroral forms, like where are they seen, when are they seen, under what conditions, things like that. So you can become an aurora scientist right now. You can submit your photos to Aurorasaurus and Skywarden, these observing platforms where scientists can then collaborate with you and utilize the great aurora photos that you take to do science. There's tons of citizen science projects as well, not just Aurorasaurus. And a fun opportunity, really exciting actually as well, is this FRAM2 mission. It's kind of under the radar. I'm surprised that more people aren't talking about this, but SpaceX is going to send astronauts in a polar orbit, and on board is a cinematographer who will be recording the aurora from above. And I'm collaborating with some researchers to organize a citizen science campaign, a participatory science campaign, where we have aurora chasers underneath the path of this mission, of this capsule, recording the aurora from below. So if we can get an image from below and above and kind of overlay them, we can get a better 3D picture of the aurora. And the goal is to photograph one of these rare auroral forms during the launch. So with that, it's 55 right now. I have a bunch of show and tell just quickly run through. I have a bunch of show and tell just quickly run through. I've been doing aurora photography for really the last 4 years. So this is sort of in the beginnings, one of these Steve phenomena. This is really the show that blew me away. That's what I call this one. March 5th, 2022. This is a real-time video of the aurora, just incredible. if you haven't seen this before, you just have to see it. It's just life-changing. Just a lot of auroras in Churchill. Did some aurora chasing up there in March of 2022. Here's some photos from that. Just another world, completely than what I get in Fairbanks. I mean, the auroras are more or less the same, around the world, but if you're underneath the auroral oval, but the landscapes is really what adds to it. And here's in September, totally different in the fall, no snow. Here's an abandoned rocket range that they were actually planning on building a spaceport in Churchill that never came to fruition. So they have all this sort of half-finished stuff up there, which is really interesting. And here's a substorm from March 23rd of last year. A really nice storm up in Fairbanks. So let me just orient you here. This is, we're looking south here, or sorry, we are looking west. South is on the left, north is on the right. So you're actually seeing this growth phase arc right here that will then form beads. I don't know if I have the exposure to show the beads because this was really quick. I think I'm at 5-second exposures here, but when the aurora is really going, I mean, you can shoot all the way as fast as like one second, 2 seconds. So, but you can see a poleward expand. So north is to the right here. So that poleward expansion happens, and that substorm had some blue aurora there as well, which is really cool. And then, hold on. So here's just some highlights of the 2024 aurora chasing season so far. Haven't edited much from the last few weeks. I've been so busy with school, but I mean, it hasn't stopped. This was in October, but we just had such a great year so far. It's incredible. So, with that, I'm going to leave a few minutes just for wrap up, but thank you all for your attention. I know that sort of towards the end, I had to skip through a few parts, but you can only cover so much in 2 hours, and I could keep going, but I want to respect everyone's time. If you want to receive this talk, it'll be emailed to you in a number of ways. I think there's going to be a follow-up from the AAA with a recording of this presentation, but I will also send out an email through my own channels with the recording, and I'm writing a blog article right now that's sort of summarizing all this in kind of a readable format, and I'll also include a link to the presentation, these slides, so that you all can have them. I'll annotate them with some links as well. So if you like to just click around and sort of explore things on your own time, you can do that. So yeah, with that, thank you all for your attention. And I mean, I can stay on longer to answer questions as well, but thank you all for attending this webinar.
Well, let's plan on that, Vincent.
Yeah.
We're not under a rush here. We can definitely
Right.
go 15, 20 minutes more for
Sure,
Q&A.
yeah, it's fine with me.
Fine. So I urge you to go to this Q&R code and to see his website, which is really quite a remarkable website, as remarkable as he is. Let me just say, can you get rid of your, can you stop your share now?
Sure.
Thank you. I just want to wrap up with my end of it, and then we'll go to end with
Sure.
Q&A, okay? We'll end with Q&A. Well, one good Q&R deserves another. I'll leave this up for a few moments. I hope it's on your screen there. There it is. If you have your cell phones out, you can take a picture of this. This will lead you to what I showed you at the start. It'll lead you, actually, to tell you the truth, it goes directly to our donation page. So if you have been impressed by our organization and would like to help support our goal of enhancing astronomy education worldwide, and especially in New York, please, we would appreciate what you can do for us. Also, if you go to this Q&R site, besides the donate page, you'll see some of the standard offerings that we have in the AAA.org, AAA.org. There's one small thing I wanted to point out. When I showed you our website, AAA.org, I showed you many buttons that you can go to for classes that are coming up and lectures and so on. If you're in the New York area, you can even see where we will have our viewing sites. What that website does not clearly show with a button is that we also have smaller dedicated groups, narrower groups that want to study one particular aspect of it. We have one group, it's an award-winning group known as the Astrophotography Group. It's led by Stan Honda, a photojournalist who is an expert in astro imaging. And that astrophotography group is part of our mix. And that particular group is planning, since Vincent mentioned it, that particular group is planning to give an entirely new talk. It'll be different than the gateway talks, which are the remote telescopes we operate. Go to the website to learn about that. But they will be offering in January a talk probably to be called Smartphone Astrophotography 101. Smartphone Astrophotography 101. Where will you find that? Our website, go to classes, it'll be listed there. If that is of interest to you, that you are a smartphone user and you would like to use it like Vincent showed us for capturing events that occur in the sky, including, of course, Aurora. They will teach you how to use your smartphone for planets, stars, the Milky Way, the Aurora, and time-lapse trails, star trails, as the night goes by, as the stars move in a circle around the sky. So learn how to capture these images using your smartphone. And after tonight, you will be receiving from the AAA a thank you for joining us. We appreciate that you gave this time to us, and asking for your consideration, should you wish to, for our efforts here in the AAA. I believe that is all I have to say for my commercial. And I urge you to go to his website, go to the AAA.org, and see what we stand for, and perhaps help us both out. Okay. Vince, it's yours again. By the way, at the start tonight, Vincent happened to mention that he gave a talk once where he forgot to press the record button. And so he told us that he actually went back to his hotel room and did the whole damn thing over again.
I did, yeah. I've done that.
You won't
I've done
have
that
to
more
do
than
that
once.
tonight. My God, what an effort that would be. My God. But thank you so much. And we look forward to your answers in the next 15 minutes.
Yeah.
And then you can sign off. And Chirag is there, my assistant or my co-host here, who's also a board member, to help comment. Okay,
All
take
right.
it away.
Yeah, sure. So I'm just gonna run through the questions, and then if I have any slides, I'll just project those. So yeah, thank you all again. Just thank you all for joining. And if you have any questions, I'll try to answer them in the next 15 minutes or so. I do have to hop off at some point, but yeah, thanks again for the AAA for allowing me to present here tonight. Really appreciate it. All right, let's jump right in. So I'm just scrolling up all the way to the top, and then I'll kind of go down from there. So I already addressed the aurora making a noise. So stable auroral red arc phenomena typically occur. So this is a question from Jim Hammond. Typically occur after substorms. I'm just going to project my screen since we can look at one of those here. So yeah, these SAR or SAR arcs typically occur after geomagnetic storms. which you can see down here, and they appear as bright red arcs. They're typically not visible to the naked eye, although really strong ones can be. In fact, we saw really strong SAR arcs during the May and October events. So if you saw really red aurora, especially overhead from lower latitudes like Oklahoma, let's say, or Texas, you may have seen one of these SAR arcs. So anyways, yeah, these typically occur after big substorms and can evolve into things like Steve or strong thermally emission velocity enhancement. And these SAR arcs, are really formed by hot flows of gas, and that's kind of this similar mechanism by which Steve is formed. These things called subauroral ion drifts. And I'm not, a really, I guess, not super knowledgeable on the generation mechanism of SAR arcs, but since they evolve into Steves, a lot of scientists think that it's a case of just this really hot flow of gas becoming so hot and so intense that the color of the emission changes from this red emission to this kind of white hot, like if you imagine like a white hot metal glowing sort of emission. So that's what a SAR arc is, and they're really, really cool and relatively unknown compared to other auroral forms. So if you've imaged a SAR arc or have any observations of SAR arcs, feel free to upload those to Aurorasaurus or even email me. I'm always looking to see more SAR arcs. I think they're really cool. So yeah, thanks for that question. I already addressed the question about the 11-year solar cycle. Are there yellow auroras? Yes, there are. The Dungy, yes, so it's spelled Dungee, cycle and dance. I don't know if I have a video of anybody doing that, but I'll try and look for that. Orangey color in my aurora picture, what causes that? I also saw pink and green. So yeah, the main auroral colors are again, this sort of light pink / purple caused by the nitrogen at lower altitudes, and then the three sort of main colors, which is the green, the blue / purple, and the red. So really anything in between is going to be due to a mixing or just the effect of like atmospheric dust and haze skewing those lighter colors towards the horizon to more darker colors, like a green to a yellow, for example. How is a white aurora created? Yes, so there is a thing called white aurora or continuum. So I think I was just going kind of fast, but in Steve is kind of white or mauve colored, and that's really due to the fact that it's a different process, supposedly a different process by which the light is being created. It's not necessarily electrons raining down into our atmosphere, colliding with gases, and then producing light in specific colors, but instead there's such a hot flow of gas in the upper atmosphere that it's energizing these particles. It could be the same gases, and heating them up so much that they glow white hot. So it's colors, it's basically like all the colors at once. And if you do that, you get white essentially. So it's potentially not the same process by which normal auroras are created. So that's why Steve is sometimes referred to as just an aurora-like phenomenon and not actually an aurora. So besides the white aurora, quote unquote, aurora in Steve, there's been some research that's shown that these white auroral emissions, these continuum emissions, are more common than we initially thought. So I'm actually a co-author on a paper that is really investigating these white auroras that we see in Svalbard in some of the imagers up there. So it's really interesting, and something that, yep.
No, go ahead. You finish.
Oh, I was just going to say that it's just one of the things that participatory science is really hoping to investigate, is these white or continuum auroras.
Oh, that's fine. I had a question regarding what's the advantage of using ghost magnetometers
Yep.
versus ground-based magnetometers, especially
Yes.
close to us.
Yep. So ground-based magnetometers are, I think, even better than GOES, honestly, because you can see the growth phase in the magnetometer a little bit better. But I like the GOES magnetometers because in some places you don't have ground magnetometer coverage. So the ground magnetometers are kind of only giving you the magnetic fields at a specific location on Earth. So you might have a chain of magnetometers close to your house, which can help you. But a lot of times apps and things like that are relying on magnetometers that may be far away from you to predict, what's happening on a global scale, which works in a lot of cases. But I just like the GOES magnetometers because they're relatively intuitive, compared to ground magnetometers. And I'm kind of transitioning. I like to really dive deep into one thing first, learn a lot about it, and then move to the next. So I've kind of done that with the GOES magnetometers, but I'm still learning a lot about GOES magnetometers. So I do want to, and I do use ground magnetometers to some extent, but I still really rely on GOES mag, because that's the one thing too, is that GOES magnetometers are not useful for anybody not in North America, or useful for anybody outside North America. So yeah, those magnetometers are geostationary, on satellites, geostationary with the east and west coast of the US. So ground magnetometers obviously work better than GOES for places like in Europe and Australia and all those other locations. So I need to write some sort of guide on that at some point, but yeah.
Thanks.
And then I'll just, okay, what is a solar cycle? What physical changes happen to the sun during a solar cycle? I'll quickly answer this one. So the sun's magnetic fields flip orientation, and then during that flip, you get all sorts of wild magnetic fields that form. So if you imagine like a bar magnet and like the magnetic fields, and you start twisting them around, you start getting like knots and lumps and kinks, and those kind of form your sunspots and active regions. And then after a while, they relax and kind of go back to that dipole state. Yeah, color scene. Say it again.
I think there's some interest on like taking pictures of photography guidelines for that. So there's some questions on the chat regarding that.
Oh, okay. Oh, I'm seeing more down here. Yep. Yeah. So for photography of the Northern Lights or the Aurora, yeah, it's really going to depend on what gear you have and how strong the Aurora is. I would just say, without getting too far into it, I'll just share my screen so we can get through this, go through my presentation, because I do have some slides on that. I will go to this slide. This is the most relevant. So, I was talking about how I kind of graduated, quote unquote, graduated from astrophotography, like Milky Way photography, to Aurora photography. And, besides being a lot harder to see the Aurora than the Milky Way, right? The Milky Way is always there. In the Aurora, you have to kind of forecast space weather and understand what's going on. The Aurora is harder to photograph just objectively because it's not the same brightness every single night, let alone every single hour, minute, or second. So, one thing you have to keep in mind is that you might have to change your shutter speed to a lower or like quicker value to capture some of the fine scale structure in the Aurora, especially when it's really, really active. So like, for example, in this shot here, I was at 1.6 seconds and ISO 640, which is pretty low. For most people, when they think about astrophotography, they think about like 1600 to 12,800 or something. But this was fairly low, and it's because the Aurora was just so bright. So you really need to be able to react with your camera settings to when the Aurora gets really, really bright. And a common strategy is to slightly underexpose, especially if you're doing a time lapse, is to slightly underexpose your shot so that you're able to capture the Aurora when it's really, really bright without having to stop the time lapse and adjust your settings, or shoot in some sort of program mode like manual mode with auto ISO. So. All right. Stop sharing so I can see the Q&A. Okay. I know people probably want me to answer all their questions. There's so many in here. I'll just answer two more. Does that sound good? And then if people have questions too, they can always email me. I guess I'll have some time because I'll be going home for Thanksgiving break. So I got some time on the plane. So I'll try and respond over the next few days. But it's just Vincent@theauroraguy.com. And there's even a contact form on my website. Okay. Do I alert if a substorm is coming? I try to. If I am not doing homework and I'm paying attention to GOES, I'll post on social media if there's a substorm. And then I think I saw something about, research being done on cones and rods and animals and how they may see aurora differently. That's really cool. I don't know if people are doing research. I mean, whether or not animals even react to the aurora, I think is an interesting question. I bet that they do because, the aurora can be not only very bright, but also during geomagnetic storms. In fact, the magnetic field perturbations and changes in Earth's magnetic field can be disturbing for like birds, for example. So fun fact is that one of NOAA SWPC, Space Weather Prediction Center's customers for space weather alerts and space weather products is like the National Pigeon Racing Society, because pigeons are so sensitive to magnetic fields. So when there's any kind of geomagnetic storm, they may not do what they're supposed to do during these races. Links to all sky cameras. Yep. So those are on my website under, so if you go to resources and then webcams, I just have a huge list. I'm actually working with a developer right now to build that out a little bit better. So stay tuned, because I'll have like live updating pictures on the website instead of just a big list of links. So yeah, I guess with that, if people have any other questions, they can email me, or we can just do it that way. So since it's about 15 after the hour, does that sound good?
Yep. Thank you, Vincent.
Thank you very much again. And thanks all for coming and joining us. Hope to see you at some future event. Good night, all.
Right. Thank you so much, Vincent. This was super.
Yeah. Yeah, of course.
Take care.
Thanks.